We have all dropped something and watched it fall. Here on Earth, that object accelerates toward the ground at exactly 9.8 meters per second squared. That 9.8 is a physical signature, a value coded by the specific geometry of our planet. To understand where that number originates, we have to look past the idea of Earth as a solid rock. Instead, we can model the planet as a massive onion, built from hundreds of thin, concentric spherical shells. By mathematically peeling back those layers, we can isolate the specific sequence of gravitational forces acting on us. This calculation provides the data necessary to weigh the entire world. Consider dropping a test mass down a deep mineshaft, stopping at a specific distance from the center, radius r. Physics dictates that any planetary layers outside this radius cancel out to zero net gravitational force. The gravitational pulls coming from the various regions of those outer shells act in every direction simultaneously, resulting in a perfect cancellation. Consequently, the mass feels no downward pull from the rock above it. It is attracted only by the mass contained entirely within its current radius. The formula for this internal pull is written as force equals g times m sub r times m divided by r squared. Here, g is the gravitational constant, m sub r the inner mass, m the test mass, and r the distance to center. Assuming uniform density, we substitute the inner mass. The formula shifts. Force equals g times m times Earth's mass times r divided by Earth's radius cubed. Deep inside the planet, gravity functions as a linear tug-of-war, determined solely by the volume of mass directly beneath you. Bringing the test mass back to the surface crust, the entire Earth's mass is beneath it. At full radius, the math simplifies to the standard surface formula. Force equals g times Earth's mass times the object's mass, divided by Earth's radius squared. Substituting Newton's second law, F equals mg, into our equation, the test mass m appears on both sides and crosses out. This proves acceleration is independent of an object's weight. Our final relationship remains little g equals g times Earth's mass divided by Earth's radius squared. This newly derived equation left physicists with a calculation containing only one unknown value. Little g is easily measured by timing a falling object, and the Earth's total radius was already a mapped known quantity. In 1798, Henry Cavendish designed an experiment that finally filled that gap. Cavendish's primary objective was to establish the numerical value of g, the universal gravitational constant. He utilized a highly sensitive torsion balance, a suspended bar with lead spheres on each end, to measure the incredibly weak gravitational attraction between physical masses. By establishing the value of g through the torsion balance, Cavendish isolated the final variable in the surface equation. By rearranging the formula to solve for the Earth's mass, we can multiply g by the radius squared and divide by g. The metric of 9.8 meters per second squared provides the calculation required to weigh the entire world without ever leaving its surface.